So we've been talking about olefin metaphysis, and we've been working through the mechanism of that. Remember, metaphysis is just, in terms of the what of the reaction, it's pretty simple. You take two alkenes, and for this reaction to be useful, it's usually two of the same alkene if it's an intermolecular metaphysis reaction. And we're going to pay attention to the internal carbons versus the external carbons. Metaphysis is really only going to be very useful for terminal alkenes. And there's a question in your study guide or practice exam that has you basically convince yourself why. If you try to do metaphysis on two different alkenes, you're going to get all possible combinations of both carbons of the alkene. So it's really only useful when they're terminal alkenes, because when they're terminal alkenes, there's a driving force to take the two terminal CH2 groups, link them together so that they are ethylene, which is a gas that comes out of the equilibrium, and that drives the reaction to completion, where the two purple carbons end up bonded to each other. All right? And the catalyst is, this ruthenium complex called the Grubbs catalyst, and there's multiple versions of this. There's some other catalysts that work here too. We were talking about the mechanism, and this one's involved because there's so many things that have to happen to break the two bonds, the sigma and the pi of one, and then the sigma and the pi of the other, and then make a new sigma and pi with the two of them. So I tried to show you last time about how a pre-catalyst was generated. This is what you put in the reaction. Cy here equals cyclohexane. And right now the ruthenium is coordinatively saturated. You need to lose one of the phosphine ligands so that you can bind an alkene. And then this unusual 2+2 reaction occurs. And what we're basically doing is trading two pi bonds for two sigma bonds, which should be thermodynamically favorable since sigma bonds are more stable than pi bonds. Essentially, we're moving these pi electrons to become a new bond between carbon and carbon, and these pi electrons to become a new bond between carbon and ruthenium. This generates our four-membered ring, which we called a metallocycle. I'm going to label the carbons of our olefin like we did above in considering what happens. Here's purple, here's yellow. Here's still purple, here's still yellow. After we make the metallocycle, we can do the retro 2+2, where again we're going to trade two sigma bonds for pi bonds. So we could move these electrons in this carbon-ruthenium sigma bond to become a new ruthenium-carbon pi bond, and the electrons in this carbon-carbon sigma bond to become a new carbon-carbon pi bond. Now, if you're paying attention to what happened, we just made something that we have no intention of making and no intention of using. That is, we took this carbon that was originally in the catalyst, and now we've linked it to the purple carbon of our reagent. And we've now got the yellow carbon of our starting material on the ruthenium. This is a byproduct that we don't worry about, because this is a catalytic reaction, so we're only adding a very small amount of catalyst relative to starting material. So you only need to do this once to generate an active catalyst. And so the byproduct forms in a vanishingly small amount, and therefore we don't worry about it. Once you get to here, this is your active catalyst. So this is the yellow carbon from our original reagent, and then here's the yellow terminal carbon from the second unit of our alkene, and here's the purple internal carbon. Again, we're going to do the 2 plus 2, trading 2 pi bonds for a sigma bond, for 2 sigma bonds. See, we've now made a sigma bond between yellow carbons, and we're making a pi bond between purple carbon and ruthenium. Sorry, I'm getting ahead of myself. We're trading a pi bond for a sigma bond between yellow carbons, and this pi bond for a sigma bond between ruthenium and carbon. We again get this metallocycle, and then if we do the retro 2 plus 2, we put our purple carbon onto the ruthenium, and then we have made our first product, which is ethylene, which bubbles off as a gas. So notice all of that was to get so that we've made this. We haven't made this yet. We haven't made the olefin where the 2 purple R groups are linked together. All right, so we're sort of halfway through. Questions so far? Yeah. Yeah, I should definitely move the little gray box. Or I should try drawing stuff immediately behind it to drive you crazy. Come on. Okay. That's weird. Still there? No. Okay. All right. Questions about what we've done so far? Did you see all that stuff down below? All that stuff I'm going to make you memorize for the test? No. In fact, all of that stuff's interesting, but won't be on the test. So I was talking with a few of you yesterday in the office and telling you that, saying that I was going to talk about some things that weren't on the test, and I was trying to figure out whether that would be good or bad. I think you like it when you're not responsible for stuff, but on the other hand, you have busy lives, so why are you going to stick around if I'm telling you stuff that's not on the test, right? So anyway, we're going to talk about plastic in a minute, but all right. Once you've got the ruthenium with the purple carbon on it, we can bring in another of our alkenes. And again, we're going to do a 2 plus 2 cycloaddition. We can continue to label carbons. So make a new sigma bond there, make a new sigma bond there. This gives us our metallocycle again. And if you notice what we just did, we just made the sigma bond between purple carbons. So that's one of the 2 bonds we had to make. And then we can do the minus 2 plus 2. That's going to involve making the new pi bond and then making this new pi bond as well. That gets us to our product, and because these steps are equilibrium steps, we're going to get the most stable configuration of the alkene generally. And then notice what we've regenerated. Conveniently, once we've made both sigma and pi bonds in our purple olefin, we regenerate the active catalyst. So we've just gone through one cycle of catalysis. So this would be 1, 2, 3, and 4, and then you can continue to crank. Okay? And each time you get back to the active catalyst, you have the olefin bind the ruthenium in this way so that you can make a new sigma bond between yellow carbons. The thing that pulls this reaction around is the fact that when you make ethylene, it removes itself from the equilibrium. All right. Yes? Is the product always trans? In not cyclic molecules, yes, usually, though I'm not going to push you on stereochemistry there. For cyclic molecules, it will be whatever the cycle can best tolerate. So I believe we talked about 1, 2, 3, 4, 5, 6. Maybe doing ring closing metaphysis using the ruthenium catalyst, which I'm just going to say GRUBS. And again, the best way to predict GRUBS catalyst or ruthenium metaphysis, olefin metaphysis products is just to find the two terminal olefins. Imagine splitting those two bonds in half. You get rid of the yellow carbons as ethylene, then you count the remaining carbons, 1, 2, 3, 4, 5, 6. That's now going to be a 6-membered ring with new carbon-carbon sigma and carbon-carbon pi bonds between 1 and 6. And it's going to be a cis double bond in this case because a 6-membered ring can't tolerate a trans double bond. Some of you, I'm not going to push you on this, but some of you are going to wonder, what is the minimum ring that can tolerate a trans double bond? 8. An 8-membered ring can tolerate a trans double bond, but that's not particularly important. You can also now do some things in a retrosynthetic sense. So if I were to draw this horrible thing, could ask the question, could you make that via metaphysis? And what would the starting material have been? So identify the olefin, imagine splitting it in half, and then on either end, you're going to need to tack on a CH2 group because, of course, the other product here for effective metaphysis would have to be ethylene. So it's literally Lego chemistry. Pop these two apart, link yellow to purple and yellow to purple. And it may be easier for you to just continue to draw the molecule in the same basic shape. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Got to convince myself I've got the right number of carbons. 3, 4, 5. And here's the terminal CH2 group. And then on the other side, I've got 1, 2 after the oxygen. 1, 2, the methyl group, and then a CH2 group. Okay? See how we thought backwards? All right, so the what here, once you know what you're looking at, the what happens here is pretty easy. The challenge is just, the challenge in making rings is keeping track of the number of atoms in the ring. Okay. Lastly, I guess I just want to mention something we've done in my own research. We had a protein. It's tough to draw proteins, but the protein was a short 30 amino acid protein, and it basically had this kind of structure. So there's a beta strand here, and there's a beta strand here, and another shorter beta strand there. So this is a Betasheet protein, and a lot of beta sheets are not very soluble in water because they tend to have nonpolar residues, and so the fact that this one has made it a useful model for working with beta sheet proteins. This happens to be called the WW domain. It's a particular kind of structure that's found in multiple proteins. This is one from the human protein pin 1, which is a peptidylproline isomerase. That's not important. Don't worry about memorizing it. But I told you earlier that people had worked on stapling of alpha helical proteins with via olefin metaphysis before, and how that had been important in some drug development. And the rules for doing this within a single alpha helix were pretty well worked out, but nobody had applied it yet to a beta sheet type protein, or at least not in a systematic way. And so we started to ask some questions, one of which was, let's take 2 amino acids in this particular part of the protein. I think one was 16, the other was 19. That's their relative positions in the sequence, just so you can get a sense for how far apart they were. And we linked them together via dang, I'm going to have to draw a bunch of carbons here that 1, 2, 3, 4. And then, oops, sorry, there was another carbon there. Okay. That's roughly the size of the staple that we made. We put these long PEG chains. These are alternating 2 carbons and oxygens, polyethylene glycol. But anyway, we had this sort of neutral but fairly polar linker, and then the stapling position. And we did that staple via metaphysis. And we asked, what is the stability of the protein if you measure how stable the protein is with the crosslink versus without the crosslink? What's the difference, and is it measurable? And the way you measure stability of proteins is really, at least in my lab, is there's a spectroscopic technique called circular dichroism, where you can see a spectrum that tells you whether the protein's folded or not, and then you turn up the temperature and you watch that signal go away, and that ends up being a curve that looks like this, that you can fit the data and determine what's called a melting temperature, and you can also calculate a free energy of unfolding or folding. And that tells you how stable the protein is. And we did this for both of these and then compared how stable they were. And the difference in folding free energies was around minus 0.25 kilocalories per mole. Now, that's really, really small amount, and it's not much stabilization at all. Remember the rule of thumb that at room temperature, about 1.4 kilocalories per mole is worth a factor of 10 in equilibrium constant. So these are, even though we made the covalent linkage, these are basically similar in stability. Why would we have expected a staple to make a difference? Well, the answer is that the unfolded protein is thought to be sort of disorganized. And if you make a covalent constraint between 2 spots that are not close in sequence, but are close in the folded tertiary structure, then you are paying some of the energy it takes for folding to occur. Going from this state to this state involves a loss of translational, rotational degrees of freedom, as the side chains and the backbone have to have a specific orientation. So if you lock them together ahead of time, you've already paid for a lot of that, and you can observe an increase in stability. So why didn't we see a huge increase here? And the answer is these 2 positions are only 3 amino acids apart. They're close in tertiary structure, but they're also close in sequence. So there wasn't a lot to be gained by putting the staple there. So Principle one is if you're going to staple a protein, your staple positions need to be close in the final structure, but far apart in sequence. So we tried again. This is how science actually works. You do something, it doesn't work, and then you say, we will try again. And you try again, and it still doesn't work, and you continue to try again. And eventually you get it to work, or you just give up, which does happen sometimes. So we thought, let's repeat the experiment, but instead of using positions that are close to each other, let's try in primary sequence, let's try positions that are far apart in primary sequence. So, oh, that's loud. I'm being urged to upgrade to Monterey, and Sophos is asking for full disk access. I'm sorry about that. Anyway, these two positions don't look like they're close to each other, but they're actually maybe 10 angstroms apart, only a nanometer apart in the folded structure. And so I'm not going to draw the structure of the staple, but basically we installed a staple between those positions, and then we asked, and we did it via ruthenium metaphysis, olefin metaphysis. Then we asked, what's the difference when it's stapled versus not stapled? And in that case, it was like you've got about 1.6 kcals per mole of stability when the two positions are far apart. And that now is something to work with. That's an increase in folding equilibrium constant by a factor of 10. And why would you want to make proteins more stable to begin with? Well, a lot of people are interested in using peptides and proteins as drugs, but your body has proteases that chew them up. And if you could protect your peptide or protein from that by making it more stable, there's a chance you could have a better drug. So that's sort of one of the things we're working on. We're working on understanding the rules for optimal stapling. More recently, we've taken a coiled coil system and installed a staple between the two helices and seen what that does. So that's an application of olefin metaphysis. Okay, so end of material, right? Yes?
So would it be better than if you did position 2 and 32 since they're closer?
Would it have been better if I'd done 2 and 32? Perhaps. I mean, that's we haven't tried that, but we maybe should. We've also tested the length to see how much the stability depends on the length of the linker and the length of these arms that carry the olefin that's getting linked together. And there is some dependence on length. What we think is happening is there's some critical length that is only just sufficient to span the distance between these two positions. And if you go longer than that, you don't necessarily get a better benefit, but if you go shorter, it doesn't quite stretch. And so that can make the protein less stable. Yeah? Yeah, it's a good question. Could the staple interfere with function? Yes, absolutely. And that's why people that do this, and the most commonly used application of stapling is in the context of proteins that bind alpha helices. So if this purple blob is the protein of choice, and it doesn't matter, I'm going to give it a name just because you may learn about this at some point, MDM2, and the peptide here, and it's a helix, but we're going to just sort of be, well, it looks like a cinnamon roll. Here is your peptide helix. Usually there will be nonpolar residues at the interface between the protein and the helix. And often they will put the staple here. So you have to imagine that's on one turn of the helix, and then this is a couple of turns down, but this is the staple. They will often put it not at the binding interface because that would get in the way. But they'll put it here. Experimentally, they also tried putting it here, but they found it would work better when they put it there. I think because they're picking up additional van der Waals contacts between their staple, which is mostly hydrophobic, and the protein. So yeah, it does matter, but it's something that you sort of have to play around with, and will depend on the function of your protein. Okay, what else? Yeah. Do the staples assist in folding of the helices? Well, what you do, yes, they do, because from the beginning you've got the covalent constraint. And so, for example, in a helix, a typical staple is usually between the I position and the I+7 position. That's 7 amino acids apart. So in a linear peptide, those would be here. But in a helical peptide, they're way closer, like within 10 angstroms or something like that, whereas they'd be farther apart. And so that covalent constraint increases the penalty for unfolding. Yeah. Okay, what else? Yeah. Could you change the fold of the staple? Yeah, that's actually interesting. That's an interesting question. There's a group, I forget where they are, but they installed actually like a diazo staple, and you could control whether it was cis versus trans based on absorbance of light. And so, whoops, I'm not connecting that. That's not a really good bond. But anyway, they could shoot light here and make it convert from trans to cis or vice versa, and that would change the shape of the protein. So I can't remember how well it worked, but that was kind of the idea. Can you make a switch that allows you to change protein structure? Yeah. Okay. All right, well, I want to talk about plastics now, because of all the things that you've learned in this class, the thing that you're going to have the most interaction with probably for the rest of your life is plastic. That's the thing you've encountered the most and which you will continue to encounter the most, from the plastic water bottles that we're not supposed to use and instead actually use reusable ones, to the plastic straws we're also not supposed to use, to food packaging, to the chairs, the upholstery that you're sitting on, the plastic underneath and the lining, the carpet that you're standing on. A lot of things around you are made of plastics and polymers. So this is a whirlwind tour through polymers, but I want you to have seen it. I'm not going to ask you any questions about it, so just relax. A lot of these are made through a process called radical polymerization. And this involves usually a substituted olefin. In this case, we're starting with vinyl chloride, and you take a radical initiator and you add to the pi bond, but you make the bond with the less substituted carbon so that the more substituted carbon can have the radical. Chloro, with its lone pairs, can stabilize the radical by resonance. And then that radical can add another vinyl chloride unit, and another, and another, and another, until you have this long chain of vinyl chloride units linked to each other. And put together, we call that polyvinyl chloride, or more popularly known as PVC. Okay, you've heard of PVC before, right? This is often used in pipes and fittings, hoses, flooring, and there are different sort of versions of that. The polymer tends to be pretty rigid, and the PVC polymer tends to be pretty rigid, and in part this is because of van der Waals interactions that happen as individual units of the polymer sort of get close to each other and interact and form can form almost a crystalline state. And rigidity in PVC is not necessarily that good of an idea. For example, if you've ever had a garden hose, you want to be able to move it around rather than like pick up the solid hose and sort of try to rotate, right? So what they do is they put something called a plasticizer inside. This is a molecule that will intercalate into this crystalline domain and actually swap out, will engage the polymer in van der Waals interactions that replace the ones that were occurring between polymer subunits. And this makes the polymer way less rigid, more flexible. The problem is the polymer can leach out over time. So if you've had a really old PVC hose and it's been sitting out in the sun for a long time, plasticizer's likely leached out and you start to form cracks. Another fun experience in my life with polyvinyl chloride was one of my early years here. We had a sprinkling system in our front yard, and it was made with rigid PVC pipe. And I was told that it's a good idea to blow the water out of your sprinkler system before winter, because if you leave water in the sprinkling system during winter, water expands when it freezes. If the lines freeze, that can cause your pipes to burst. And I thought to myself, oh, it can't possibly be that bad. It would have to get really cold for the pipe that's that deep in the ground to freeze, and so I didn't do what I had been warned to do. Perhaps you've done something similar in your life where you didn't do something you were warned to do. In any case, that next spring I get the sprinkler system started up, and instead of the sprinklers popping up and spraying, the whole corner of my lawn starts to raise up and water just oozes out of it. And what had happened, surprise, surprise, is that the water in the pipe had frozen and the PVC pipe had burst. And it didn't just like crack. I mean, it shattered in this weird spiral pattern. I mean, I don't know if it made that sound, but totally shattered. So I had to spend several days fixing that. In fact, in my front lawn, there's still a big divot along this long edge of where I had to pull out a pipe, and it's a reminder of my hubris. And every year, I now blow out my sprinklers. Other polymers you've heard of. Let's see. I should mention there's a potential for branching because one radical can abstract a hydrogen to create a new radical here, and then that's a new spot for a new chain to start growing. And so branching can contribute to polymer flexibility because each branch point, it's kind of like cis double bonds in fatty acids, each branch point prevents the individual polymer chains from packing together quite as tightly. So if you use ethylene as your starting material, you can make polyethylene, or PE is plastic. That's 4 in your recycle label. If you allow branching in the process, you get low-density polyethylene, LDPE, and this is often used in bottles and containers and tubing and so on. In contrast, if you suppress the branching through an approach we're not going to talk about, but if you suppress branching, you get high-density polyethylene, or HDPE. That's 2 in your recycle label. And those are more rigid polyethylene containers, for example. I think the one that I've seen most recently is probably like a laundry detergent bottle or other things. So just look around on labels of packaging and then come back to here and see whether you recognize anything. Polystyrene we've talked about before. This is a spork. Because you can make sporks out of polystyrene. It's just like polyvinyl chloride, but instead of chloro, you have the benzene ring. It's a little bit brittle. Polystyrene is abbreviated PS. That's number 6 in your recycling label. I do remember what's with the angry spork. You have to know VeggieTales, and you have to know their spoof on Lord of the Rings, Lord of the Beans. And the sporks were the equivalent of orcs in this story, anyway. So it was a stretch. Polypropylene, methyl groups instead of phenyl groups. You may have actually eaten this polymer before. Vinyl acetate is used in Elmer's glue, wood glue, paint. I hope it was Elmer's glue you ate instead of paint. Envelope adhesive, it's considered safe so that you can lick it and still, but nobody sends envelopes anymore. Nobody licks envelopes, so that was a thing of the past. Teflon is probably something you've also ingested because you have a pan, various pans coated with Teflon, and then you go to scrape them really hard as you're cooking and some of the bits come off. Seems fairly innocuous. You start with ethylene, but you have fluoro groups on them, and you make a polymer like this. Fluorine's a little bit weird. It's not really friendly with water, but it's also not that friendly with organic solvents, so this is why it's a non-stick coating. Finally, not finally, we got more stuff to do maybe. For those of you who anticipate careers in dentistry, I present BPA glycidyl methacrylate, or BIS-GMA. This is dental composite. All right. So if you've been to the dentist before and gotten a filling, if you have never had a cavity, yay for you. But the rest of us who've had cavities, man, my 14-year-old. So whatever. So he last summer complained of a toothache. He was actually away at a youth conference, and he's texting us in the middle of the night. I'm dying. I want to die. Please kill me now. My tooth hurts. And we're like, well, for one thing, we're not going to kill you. But even if we wanted to, we're like 200 miles away. So, and he got a blessing and some ibuprofen, and then the presence of girls his age, I think, helped him sort of push through. But it turned out that the kid was in need of a root canal because his tooth had rotted all the way down the middle. And we're still, and so he dealt with all this pain, and he had to go to the endodontist, and it was really expensive. And yet he still shows up in the morning. We like, did you brush your teeth last night? And he's like, So if you have any advice as to, maybe, I know what to do. We brick his phone until he brushes his teeth, and then I could do that, by the way. Do you want to see if I get a text? Anyway, sorry. So that was dumb. I'm sorry, but if you, I didn't actually brick his phone, but. I can, and that's fun power to have. You guys know what I mean when I say brick as a verb. To brick his phone is to turn it into a brick because the apps are all disabled? No? Nobody ever says that? Okay, sorry. I'm old. I don't know the way to go. So, BPA methacrylate, here is the double bond that's involved in polymerization. And what you basically get when you polymerize is a zigzag chain where every other carbon has a methyl group on it, and then this ester, which is linked to this whole green group, which is linked to another polymer chain. So I tried to illustrate that here, and it's not at all clear, but this creates a heavily cross-linked chain, because you polymerize on one side, and then each of those can be linked to another polymer chain, and they don't have to be linked to the same one. And so you get this really interconnected network of linkages, and that causes the dental composite to harden. The way you initiate this is actually through UV light. So if you've been in the dentist chair and they stick this gun in your mouth, and at the end is this really bright light that you're not supposed to look at, maybe they'll put some sunglasses on, and you see this little yellow things around the behind the gun to shield their eyes from the UV light. What they're doing is they're polymerizing your dental composite, causing it to harden. It happens really, really fast. So some of you will have occasion to do that in your future. Hopefully as the compositor rather than the compositee, so brush your teeth, friends. You may have seen something familiar in the name BPA glycidyl methacrylate. BPA is called bisphenol A, which is this molecule. Looks relatively innocuous. It's used it's been used before as a crosslinker in a lot of different polymers, because cross-linking can increase polymer rigidity and strength. But you may have heard a lot of talk over BPA plastics, BPA cans. Cans metal doesn't have BPA in it, but the polymer lining inside the metal does. Why would you want to not have BPA in your plastic? Well, it turns out that BPA sort of looks kind of like estradiol, which is estrogen. Here's the two OH groups, and they're about the same distance apart. It binds estrogen receptors with about 1,000 to 2,000 fold reduced affinity than estrogen does itself. So it's not nearly as potent, but it's enough that it's a concern. And especially with infants who are nursing from bottles, in some cases, and you don't want them to you don't want to mess with their hormones, even if there's a small chance. And so that's why you can't have BPA in baby bottles anymore. BPA is a starting material for a lot of epoxy resins and polycarbonates. As I said, the FDA bans its use in baby bottles, and its effects and the risks are still controversial. So there's something you'll hear about called the precautionary principle, which is this idea that if there's even a tiniest risk that a chemical may be dangerous, it's best not to worry, that it's best not to use it, and there's still ongoing debate about that. All right, well, that concludes 352. I wish you all the best. Please stay in touch. Good luck on your exam. May God have mercy on your souls, and may the force be with you. We'll see you later.